Hello everyone, welcome back to my channel. This is Kshitij, and on this channel we talk about robotics, research and academia. This is the third lecture in the lecture series TT101 Basics of Mobile Robotics. If you're new here and if you have missed the previous video, the link will be in the I button above, and in the description box below there would be a link to the entire playlist where all the lecture series are arranged in a chronological order. So let's get started with today's lecture. In today's lecture, we are introducing preliminaries. This is the brief overview of the lecture. We're going to do a quick recap of what we studied the last time. We're going to look into various state spaces that we address quite frequently when we talk about robots. Frames of references, which are an important concept when dealing with information and explaining it for robots. Transformations and kinematics and motion constraints. Previously, we discussed various types of sensors, types of intelligence, types of actuators, and primary control paradigms. All of this was a high-level overview because it was just an introductory lecture. Now, we are looking into preliminaries and notations, which would be the building blocks for the upcoming lectures. So first, we would look into various forms of state spaces. Now, what is the state of a robot? The state of the robot is defined as, let's just say for a very abstract definition, as the condition or the situation in which the robot is in at any given point in time. Okay. Now there are various ways to explain it. First, we are going to look into something called a configuration space, also known as a C space. It explains where is the robot, which is what we are interested in for the sense plan act paradigm that we discussed in last time. Now, the C space is the set of all possible robot configurations where a configuration is defined as position of all points on a robot. Let's take a look at this example shown on the left, the red block. Think of a robot as being represented by an abstract square where the blue cross in the middle marks the center of mass of the robot, and the square with four corners represents the boundary of the robot. Now, of course, a square has four corners, but it also has various points along the edges. So in order to define the configuration of a robot, you need to define what happens to all of these points at various instances, and a collection of all of those would become the C space. Robots are typically considered as a collection of links or rigid bodies and joints. Joints help connect various links to each other. And because of this rigid body assumption, what we can understand is if you understand point 1 and point 2, you don't need to worry about the points in the middle so much because the body does not deform. So if you know the position of this, you know the position of this, the points along the edge would be collinear, right? So it simplifies the assumption and reduces the dimensionality of the C space by using the rigid body assumption. Now, degrees of freedom is another important concept for defining the state of a robot. Now, the robot's ability to achieve various poses is what is defined by the degree of freedom. More formally, it defines the dimensionality of the C space. Degrees of freedom are the minimum number of real numbers required to represent the configuration of a robot. So it could be 1D, 2D, 3D, depending on various scenarios. Workspace is another state space that comes into picture quite often when dealing with robots. It defines the range of possible poses that a robot could take, includes all reachable configurations, which means there are certain places in the environment where the robot can and cannot go. It's just because the robot cannot do certain things. For example, if you have a car, forget about what they do in Fast and Furious like movies, but a car cannot fly in these air and flip over and jump over valleys and mountains and stuff, right? So car can drive back and forth and you have a steering to make a turn. So there are certain places where a car cannot go, which means there are certain configurations a car can and cannot achieve. So a workspace doesn't really care about what your task is, but it only cares about all the configurations that the robot can achieve. So it ignores everything that the robot cannot achieve. Similar to that, there is a task space, which is the space of all the robot tasks. So if you have a certain task and you could define it in a mathematical space, that would be the task space. Here, it does not take into account the things that the robot cannot achieve. So the configurations the robot cannot achieve would still be a part of the task space. So task space only talks about the task, workspace only talks about the robot. Now, moving on, we will talk about frames of references. So throughout robotics, especially mobile robotics, frames of references are a very important concept. And there might be a lot of different frames that you might have to deal with. Now, if you're wondering why there are so many frames, the idea is to reason based on local reference information that you have. So for instance, if a sensor, let's say here I've shown a sonar sensor, which detects an obstacle, say 20 centimeters from the robot. Technically, it is reporting 20 centimeters with respect to the frame of reference of the sensor, which is then offset with respect to the frame of reference of the robot, known as the base frame. And as the robot moves, these frames, at different points in time will be at different parts in the environment. So you need some frame of reference that is fixed, which is often known as the world frame or the absolute frame, which you assume to be, you know where the origin of that frame is, so it doesn't move at all, it just stays there. Another thing that you have to remember is that with these coordinate frames, we often try to stick to the right-hand system. Now, in this diagram, I have shown a point P on the robot. So if you want to define the configuration of a robot, there are different points on this robot that you need to take care of. But let's just say I take one point P. This vector BP is the representation of the point P in the base frame B. Similarly, WP is with respect to the world frame. And then each of these frames have a certain relationship with respect to each other, which we know as transformations. So the WTS is the transformation of the sensor frame with respect to world frame, and then so on and so forth. So the subscript written at the bottom is the frame that you're trying to transform, and then the subscript written at the top is the frame that is used as the reference frame. Sometimes we could even write them both as subscripts. So in this case, it would become TWS, which means the transform for the sensor frame to the world frame, or it could be done this way. Now, transformations, as I was referring, so transformations not only refer to different relationships between different frames of references, but it could also mean, you want to do something with a vector you're given in space, with a point you have. You, again, want to define some relationships between the frames and so on. So transformations typically you could consider could either mean a translation where, say, a robot is still facing the same heading and it just kind of translates along one of the axes. Could be rotation where the heading of the robot is changed. So although it is shown at different places here, but what I mean is just like rotate on the spot, for example. Or it could be a combination of both, where you could rotate on the spot and then go somewhere, then rotate on the spot and go somewhere, and like it could be chained thereafter. Not only you could do rotations, you could also consider things like shearing, scaling, etc., which are more useful when you're dealing with vectors and linear algebra in general. But in robotics, primarily, you are considering rotations, translations, and a combination thereof. First, let us look into pure translations. So if you have a configuration, the original configuration of the robot, say given here by X, Y, and Z, and it could be n-dimensional, so there could be more variables depending on the degrees of freedom. In 3 dimensions, it could be X, Y, Z, or X, Y, and orientation, or whatever. And then you want to translate the robot. So that would basically mean you add an offset to the corresponding axis that you want to translate along. So for instance, if I only want to translate along the X, I will add a non-zero real value here and everything else would become zeros. Similarly, for Y, it would be a non-zero value for delta Y and everything else would be a 0, etc. And then the resultant is the translated configuration of the robot. So here's a pop quiz for you. How would you translate a 2D point 3, 5? It's the X coordinate is 3, the Y coordinate is 5. By plus 3 units along the x-axis and plus 6 units along the y-axis. And what's the resultant of this translation? Now, in terms of rotation, you have to be a bit more careful because you should understand that the rotation could happen clockwise or counterclockwise. So unless otherwise stated, the default is assumed to be counterclockwise. The only difference is the angle is given a negative sign when you start talking about clockwise rotations. So we try to keep positive angles to remove any confusions, and then we start talking about counterclockwise rotations instead. So here, let's say you have the amount by which you have to rotate, represented as a rotation matrix, which we're going to look into in just a moment. And then you multiply that with your original configurations, then you get your rotated configuration after. Sorry, this is a typo, not translated, it's rotated. Okay, now before we look into rotation matrices, we are going to first look into various ways of representing rotations and then how you develop a rotation matrix out of that, right? So first would be Euler angles. So if you haven't heard about the roll, pitch, and yaw, you're gonna use it quite frequently, I guess, when you start dealing with robots. So roll, pitch, and yaw, as you can see in this figure here, although it is shown for aerial vehicle, let's say, it is also very common for ground robots or for any other mobile robot. In 3D space, you could have roll, which is rotation about the x-axis by an angle phi, pitch, which is the rotation about the y-axis by an angle theta, and yaw, which is the rotation about the z-axis, which by an angle psi. Okay, so in short, these are called roll, pitch, and yaw, or theta, phi, and psi. Now, any rotation. So Euler has this theorem which says any rotation in 3D space can be described by 3 successive rotations about linearly independent axes. So here x, y, z are linearly independent axes, and if you want to come up with the rotation, you could decompose it into 3 successive rotations that gave you that resultant rotation, which means you could have different kind of types of Euler angles, rotations, which would mean x, y, z, which means you rotate about the x first, then take the result and rotate that about the new y, and take that and rotate about the new z. Same way you could go on for z, y, z, yada, yada, yada. So you could just, there are multiple combinations of this. Now, one caveat here is there you have to be careful with this singularity that appears when dealing with Euler angles. So because you're doing 3 consecutive rotations, sometimes it might be a case that one of the Euler angle drop down to 0. This is also known as a gimbal lock, in which you suddenly lose 1 degree of freedom. And although there should be 3 degrees of freedom here, the roll, pitch, and yaw, 2 of the axes become collinear, which violates this description that the 3 axes needs to be linearly independent, which means a lot of your information gets lost along that 1 axis, and you're just left with 2 degrees of freedom instead of 3. So there is a singularity with these Euler angles. If you want to make a rotation matrix out of that, we're going to quickly look at how you come up with this. It's basically you're going to end up with an entity like this. So in 3 dimensions, you're going to get a 3 by 3 rotation matrix. And if you want to rotate by an angle phi along the axis x, it's written as such, where these are the components of projected components, and this line of 1s and 0s basically represents that no change happens along that axis, because that's the axis of rotation. So if you have a vector that is directly collinear with the x-axis or even parallel to it, it will undergo no change, but everything else will be affected by this amount. It will be rotated by the corresponding amount. Similarly, for y, you have no change along the y and no change along the z respectively for the rotation about z, but everything else you get like a rotation component accordingly, which defines the amount of rotation there. Now, so these entities that you're seeing here, 3, 4, and 5, are rotation matrices. Now, how did I come up with the matrix like that? As I was saying, you have to deal with projections. So consider a scenario here where you have the world frame in blue and the, let's say, the robot base frame in red. Now, don't get confused with the length of the arrows here. I have had to shrink the arrows for the red ones just to make it clear, but they are both unit vectors and they are representing the axes, okay, corresponding axes. And I have aligned their origins. It's just that the base frame is oriented a bit differently with respect to the world frame, and we want to understand how does this orientation relate to each other. Now, this is the beauty of rotation matrices. So if you want to deal with, understand how the 2 frames are oriented, you basically represent their transformation in the form of a matrix. So, and the notation convention here is that the hat represents, it's a unit vector, so it's already normalized. The subscript represents the frame of reference in which the corresponding unit vector is being represented. So then we want to understand what's the unit vectors of the frame B with respect to the frame W. And that can be given as follows. As I said, this is another way of representing the vectors and the frames. So if I say x hat of WB, which means the representation of x hat from the base frame B to the world frame W. Now this is given by 0, 1, 0. That's the unit vector. So you can see that it has no no component along the xw, no component along the zw, and it's collinear with yw. Hence, it is 0, 1, 0. Now, y hat of wb would be the same way. If you resolve this, then you would see that you have it's 180-degree offset by x hat of w, and then no component along the other axis. So that is represented here, 180-degree offset, no other components, and so on. So you get the three basis vectors. Now, in order to make a rotation matrix, you simply stack them. These are column vectors, so you stack them one next to each other, and that results in a 3x3 matrix, which is known as the rotation matrix. And this is how, if I go a few slides back, this is how I was getting these rotation matrices for the Euler angles, where you want to rotate by an amount phi along the axis x, amount theta by about the axis y, and amount psi about the axis z. So rotation matrices are a neat way of understanding the transforms by just dealing with matrix manipulations. Okay. So similarly, before we saw about translating a point, so now this is an exercise for you to try and figure out how you rotate a vector 3, 5 by an amount pi by 6 radians about the x-axis. Okay, so what qualifies as a rotation matrix? Not every 3x3 matrix becomes a rotation matrix, and there are certain properties that it needs to satisfy. So first of all, the group of all rotations in the R, which belongs to R3, are called a spatial orthogonal group, SO3. Now, it is special because the determinant of R should be equals to +1. It is orthogonal because, as you saw, when we stacked the columns, each of the column was orthonormal, which means if you take the dot product between any two columns, it would be 0 because the axes are orthogonal. And it's orthonormal because they are unit vectors, they are already normalized. Okay, so that's why it needs to be an orthogonal matrix, or actually orthonormal matrix. And it follows the closure property, which means if you take the product of rotations, that would still be in SO3. If you invert the rotation matrix, you will get a transpose. And if you take the transpose of the rotation matrix multiplied by the original rotation matrix, you end up with an identity matrix, which is somewhat similar to an undoing the rotations. Rotation matrices need to preserve the distance, which means if you have a rotated vector subtracted from another rotated vector, it's the same as the two vectors if you directly subtract them from each other. They also preserve the orientation, and you need at least 3 real numbers to represent rotations in SO3. Okay, that's why we had the roll, pitch, and yaw, for example, the Euler angles. They are associative, which means if I multiply RW, which is, let's say, the rotation with respect to the world frame, with the rotation with respect to the sensor frame first, and then I multiply it with the rotation with respect to the base frame, it's the same as saying if I multiply RW with the resultant of RS and RB. Although you need to be careful that they are not commutative. If you take RW, RS, RB, it's not the same as doing it the other way, RB, RS, RW. The order really makes a difference. And in the previous slide, if you see here, I said they are special because the determinant is +1. Can you think of what would happen if the determinant was equals to -1? And why do we want it to be +1 all the time? It's very straightforward, but it takes a while to come up with the reason why. What happens if the determinant is -1? So give it a thought. And as before, the answers to all the pop quizzes you can mention in the comment section below. And for instance, if you're struggling with some LaTeX equation or something, you could just carve out an image and paste it there. Or if that's not possible, then you could host it somewhere and paste the link here. Or you could even join our Discord server and have a discussion over there. The link to join the Discord server is both in the description and in the channel bio, so you could find it from there. Another way of representing the rotation is the axis angle representation. Now, in this representation, as the name suggests, you're going to have one axis and one angle that would be sufficient to represent the rotation of a rigid body in 3D space. Now, the Euler's representation theorem says all 3D rotations have an axis angle representation, which means you need an arbitrary axis V, which is shown by the green vector here, which needs to pass through the origin of the absolute frame. So in this case, we are talking about the world frame, say, so it needs to pass through the origin. And if you take this Rubik's Cube, for example, is a rigid body. So if I want to explain the orientation of a Rubik's Cube in the 3D space, I just need to look for the vector V. And about the vector V, I need to look for how much is the amount of theta that I have rotated this Rubik's Cube, and that becomes the orientation. And if you look at the Rubik's Cube I've shown on the other side, it's the same logic. You take the V, you understand what's the amount of theta about the V that represents that orientation of the Rubik's Cube, and that's your axis angle representation. And again, it's a unit vector. So V, although it's shown longer here, but it's all of these are unit vectors because they need to represent axes. And V and theta together give the orientation of any rigid body in 3 dimensions, although there is one ambiguity. So if V comma theta gives the one orientation of the body in 3D space, minus V comma minus theta actually gives the exact same thing. It's like the mirror image on the other side. So there is no way of telling them apart here. Another common way of representing rotations is quaternions, which you might hear quite often, especially if you're doing graphic development. So libraries like OpenGL, etc., and Unity 3D, they prefer using quaternions. And even in some ROS libraries, you would prefer using quaternions where you're programming your robots. So a quaternion typically is a hyper-complex number, which basically means, if you remember from high school maths, your complex numbers looked of the form a plus ib, which means there was two real values a and b, and the complex number had a real part a and a complex part ib, where I was the imaginary part, right? So here it is called hypercomplex because instead of having 2 components, now you have 4. So it sits in R4 with the 4 components Q0, Q1, Q2, Q3, or sometimes they might also be represented as QW, QX, QY, QZ. But to avoid confusion with the other XYZ orientations in the other representations, I just prefer using 0, 1, 2, 3. You could even consider ABCD or whatever to keep them different and not to confuse them together. So eventually it gets expressed at Q0 plus Q1i plus Q2j plus Q3k. And again, if you want to use this to represent an orientation in 3D space, it needs to be a unit quaternion, which means it needs to, the L2 norm should be equals to 1. So if you remember from high school, I represented the square root of -1. So it needs to apply here to all 3 ijk, which is given by I squared, j squared, k squared equals ijk equals -1. So all of them needs to be equal to -1. And then if you relate it back to the axis angle representation, we are basically saying the quaternion is the same as, is related to the orientation along that arbitrary axis we were talking about, the theta, as cos of theta by 2, and is related to the vector by sine of theta by 2. And in this representation, you don't have the problem of gimbal locks. So we looked into various ways of representing orientations. So there were Eulers, there were quaternions, there were axis angle. So are they all interconvertible? Like, can you change an Euler to a quaternion, quaternion to an axis angle, and would you get a unique answer every time? Think about this and comment down below. Okay, so far we've looked at pure translations, pure rotations, and various ways of looking into rotations. Now we're going to look into something called an affine transformation, which allows you to do a combination of rotation and translation. So if your original configuration is here, you multiply that with a rotation matrix, and then you add an offset, which is your translation to it. You're basically doing an affine transformation of your original configuration, and you get a transform configuration. Now, the only challenge with this is it's not very computationally efficient because you have to do both multiplication and addition operations. So for efficiency reasons, we want to have a situation where we stick to only one kind of computation, preferably matrix multiplication. And the way we do this is by using what we call a homogeneous transform. Now, homogeneous transform is a neat algebraic trick which basically combines the translation and rotation in such a way that you only have to keep on multiplying the matrices as opposed to multiplying sometimes, adding sometimes, and then dealing with numerical instabilities. So the way this works is you make a block matrix where the top left block is your rotation matrix, as we know. So 3 by 3 rotation matrix with the elements R11, R21, etc. The top right block matrix is your translation. So it's your 3 by 3 translation column vector or column matrix. At the bottom, you have a lines of zeros, and then here you add a 1. And this is what homogenization looks like. Because if you try and expand this first row, this translation this original configuration also appended with a 1. So if you try and expand on this matrix product with this homogenized matrix here with the original, you're going to end up with the actual affine transform that we were doing before without actually having to do multiplication and addition at the same time. This is going to be all multiplication here. So this is a pretty neat trick, and we use it all the time. And there's also a way to go back from homogeneous coordinates to the original, let's say, Euclidean coordinates if need be. But for the moment, we're not discussing going back to the original coordinates. So this is another concept that you need to remember in terms of transforms. And when we talked about combination, we wanted to be clear that we do rotations first and then translations thereafter. Although this is not set in stone, what happens if you do translation first and then rotation thereafter? There might be some challenges because of which we don't do it, but it's not that it's not possible. So think about this and comment down below what you think is the reason for doing rotation first and translation after. You could also change the rotations, so there is no reason why you have to do only one rotation at a time. And if you say you want to do a rotation R1 followed by a rotation R2 to a point P in, let's say, whatever frame of choice, which basically means you are undergoing a series of rotations, each given by Ri. In this case, is just R1, R2. So would you describe the resultant as R1, R2P, or would it be R2, R1P? And remember the properties of rotation matrices that we looked into a few slides ago. So based on that, you have to pick one of these two answers. Okay, so we looked into translation, rotation, affine transforms, homogeneous transforms, chain rotation. So you basically looked into various ways of transformations. Now, transformations give you a way to, rotate a vector and to find relationships between different coordinate frames. But what if you want to undo the transformation? Maybe you're doing a certain calculation where you have to first do a transformation and then undo a transformation. In that case, you're basically talking about taking the inverse transform. So let's say T is the transform, which is your rotation and your translation, again in homogeneous representation. So T inverse would be the inverse of your transform that you did. So that would be the transpose of the rotation matrix embedded here, which in the component written as pure inverse rotation, and everything else then are the homogeneous coordinates. And for the pure inverse translation, you would just add a negation before the translation that you did, while your rotation matrix is now replaced by identity. This basically means when you are translating, you are basically in that translation part, you are untranslating or inverse translating, because say if you went 3 centimeters forward, you want to come 3 centimeters back. So that's like +3 or -3. That's what the minus sign before the deltas represent. And while you're doing this, you're not doing rotation. That's why the rotation component, the block, is represented as an identity matrix here. The same thing on the other side, when you're only doing rotations, your translations are all zeros and you're doing the inverse rotation. So your inverse rotation matrix is the transpose of the rotation matrix. Now the question for you is, if the transformation T applies rotation and then translation, in which order does the transformation gets undone when you apply T inverse? Is it the same order that you unrotate and untranslate, or is it the other way around where you untranslate and unrotate? Think about this. This would require some basics of linear algebra and how matrices are inverted. Next, we're going to look into kinematics. Kinematics is the study of all possible motions of a robot. Possible because, like I said, there are certain motions which a robot can and cannot do. What it cannot do falls under the category of motion constraints, which is something we're going to look into as well. You want to be able to express the motion of a robot in its own coordinate frame, could be the base frame, and then eventually in the world coordinate frame, based on the inputs, the control commands you're giving to its actuators. And that's what kinematics helps you. And there are two branches of kinematics, which we're going to look into now. And remember that kinematics does not consider the forces that are required to cause the motion. So for example, if there is a block that I have placed here and I want it to be there and I use my finger to push it, that pushing is the force that made the motion happen. And I don't care about these forces that are causing the motion when I'm talking about kinematics. That falls under the category of kinetics, which is a completely different field of study. Okay, so kinematics does not really care about the causal forces. It cares about what all possible motions that the robot can and cannot do. Okay, so the first branch of kinematics is called forward kinematics, which basically means if you're given a set of control commands, let's say you're given some linear angular velocity and some amount of time elapsed, say delta t, and your current configuration is x, y, and theta. Let's say I'm talking about a robot in a 2D space, and you have x, y, and say theta represents the yaw of the robot. That's a configuration of the robot. And I want to understand if I apply those control commands to the robot after delta t, what would be the new configuration p prime of the robot? So this is known as forward kinematics. So you apply control commands to a current configuration and you want to know what would be the new configuration thereafter. Inverse kinematics, as the name suggests, is just the inverse of the process. So you know your current configuration and you know your target configuration you want to attain. What you don't know are the control commands. So you want to compute what control commands should you be giving to go from P to P prime. Okay, so quick recap. Here the control commands were known. You wanted to know what the P prime was. Inverse kinematics, P prime is known. You want to backtrack. What should be the control commands you should initiate at P to get to P prime? I hope that made some sense. And as I was saying, so when you're kind of explaining some control commands for the robot to attain certain configurations, you need to be careful of the motion constraints. Not every robot can attain every possible configuration. So there are three kinds of constraints that you could consider when deciding what all possibilities are there when it comes to attaining robot configurations. So the first one are known as holonomic constraints. Now, remember we talked about degrees of freedom, okay? So there are, let's say, X degrees of freedom, and you get to control all X of them. So the controllable degrees of freedom equals total degrees of freedom. That makes it a holonomic constraint. So for example, think of a pendulum. Think how many degrees of freedom does it have in total, and how many can you control for its swinging motion? And if they are equal, you're basically having a holonomic system. However, if the controllable degrees of freedom are less than the total degrees of freedom, you have a non-holonomic system. And that could be a case where you're talking about cars or segways or unicycles. So for example, cars, this is a brain teaser for you. Why would cars qualify as non-holonomic system? How many degrees of freedom do they have in total? And how many can you control when you're sitting on the driver's seat? And that should give you the answer. Last but not the least are redundant constraints, where the controllable degrees of freedom are even higher than the total degrees of freedom. And this is a brain teaser for you to think what system qualifies for this redundant constraint setting. All right. So a quick overview of what we learned today. So we looked into various state spaces, primarily configuration spaces, which are a very neat concept for path planning, as we are going to look into it in the later lectures. We looked into various frames of references and why we need frames of references, transformations, which explain the relationships between frames of references and body configurations. We looked into two branches of kinematics, forward and inverse kinematics, and some motion constraints that explain the configurations that the robot can and cannot attain. So this again was a preliminary lecture, which was basically laying down the foundation for the upcoming lectures. And if you have any queries or something was unclear, you're more than welcome to leave feedback and ask me questions in the comment section down below. You're also welcome to join the Discord community and discuss with other learners together to engage and interact at the same time while everyone's learning. And with this, I would like to remind you to please like, share, and subscribe to this channel and hit the bell notification so that you're notified as soon as the next lecture goes live. And with that, I'll take your leave and I'll see you in the next lecture. Take care.